All right, let's take a look at question 26 in topic set 6. This one gives us a situation where we're using a bomb calorimeter instead of the coffee cup calorimeter. And we're being asked to calculate first the heat capacity of the calorimeter. And then after we calculate that, we're being asked to calculate the energy of combustion for a substance called vanillin. So let's think about this real quickly. First, we were given the combustion of benzoic acid, and we were told that that causes a change of temperature of 2.54, and we're being asked to calculate heat capacity. So basically, in this case, we were already told that we're burning a certain quantity of benzoic acid. Notice in the parentheses here, we were told the energy released by combustion of benzoic acid is 26.42 kilojoules per gram. Okay, so let's write that down real quickly. So delta E of combustion of benzoic acid is 26.42 kilojoules per gram of benzoic acid. Okay, so this is a known quantity, something that's given to you. And what they're saying is they take some quantity of benzoic acid. Remember, this is what a bomb calorimeter looks like. You have water surrounding it. And then you have inside here a reaction container. And inside this reaction container, they say they put 0.1584 grams of benzoic acid, which then gets combusted. And when the combustion is finished, the temperature of the water rises from here to here by 2.54 degrees Celsius. So they want you to calculate the heat capacity, because the reason the temperature rises that much is because the water in here and the bomb components, which is the thing that surrounds the water, all of those absorb the energy, and that causes the temperature to rise by that much. So how do you get the heat capacity of the bomb? Now, this is an important part here. Heat capacity is not specific heat. Okay, specific heat is heat capacity divided by mass. So it's very important to remember that heat capacity on its own, since we're talking about the bomb's heat capacity, we would call it C bomb, is just Q over delta T, heat divided by temperature change. So what we need to figure out here to get the heat capacity is just how much heat is released by this reaction and divide that by the temperature change. Well, we can calculate the amount of heat because we know that each gram of benzoic acid is going to release 26.42 kilojoules of heat. We also know that the reaction uses 0.1584 grams of benzoic acid. So if you multiply those two numbers, you're going to get the amount of heat that's released. The temperature of that change is 2.54 degrees Celsius. So we take the heat divided by the delta T, we get the heat capacity, which ends up being 1.6476 kilojoules per degree Celsius. Okay, so that's for the bomb. Now, this is what we often call a calibration step for the bomb, because this tells us now that every time my temperature goes up by 1 degree Celsius, that means that corresponds to this much energy that's being released to the water and the bomb calorimeter. Okay, so that's why it's called calibration. It helps us figure out how much energy it takes to raise the temperature of this bomb calorimeter by 1 degree. You run another reaction where you use 0.2130 grams of vanillin, and then your temperature now goes up by this much. The question is, what's the energy of combustion of vanillin, a second compound, per gram and per mole of that compound? The delta E of combustion would just be the same as the heat, right? So basically what we're trying to find is just the heat. Okay? And remember that earlier we had that the C bomb calorimeter is heat over delta T. So if we want to find heat, then it's just going to be C of the bomb calorimeter times delta T. So C of the bomb calorimeter is this number that we found earlier. Delta T for the vanillin combustion is 3.25 degrees Celsius. And so that's going to give us 5.3547 kilojoules. This should be a negative because that's the amount of heat that's being released by the combustion of the vanillin. But the vanillin is of a certain quantity. We only burn 0.2130 grams of vanillin, which of course immediately simplifies to negative 25.14 kilojoules per gram of vanillin. Okay, so that tells you that that's how much energy you're going to get for 1 gram of vanillin. That's one of the questions. How do I get it per mole of vanillin, which is the second question? Is your molar mass, right? The molar mass of vanillin, the formula of vanillin is given the questions, and ends up being 152.15 grams per mole. This cancels, and you're left with negative 3825 kilojoules per now mole of vanillin. Okay?